So welcome back to our next episodes. So today's episode mostly we will see the delay analysis of our CMOS inverter, which we have designed in our previous lecture. So why delay analysis is so important? Because see, anything you do, we must need to explain how fast our design can work and why it is necessary. Because if you have remember when you have studied your microprocessor, there were few instructions which are one clock. They take one clock time. There are few instructions which take 3 cycle of clock time. So if you can reduce the clock cycle, you can do in more faster way. So that's why delay analysis is very important, so that we can fix our specification, like our design will work on that gigahertz of frequency. If you give more than that, then probably it won't work. And if you remember our lecture 8 of interview preparation series, so there we have given few idea by which as a designer how we can reduce the delay, and there we have mainly three way, and that is first, reduce the power supply. There are cons, there are pro, we will see. Second was increase the size of your inverter, your design, right? And con is obvious, we need to have more silicon area. Third, the most easy one, and that is reduce the load capacitance, because if you design anything, any inverter or any circuit, it will connect to the next block, and next block will be a effectively capacitance only. So if you reduce the load capacitance, then your charging and discharging time will reduce, which will imply the faster operation of your design. So in today's experiment, mostly we will prove those things. So let's get started. If it is interesting, then don't forget to like this video, because this video are getting very less view. So if you keep on liking, then it will motivate me to keep on doing this type of videos, right? So you can see here, these are things I have started from the last lecture only. This inverter test was our test bench. So let me go there and let me open it, but we will open it from Xschem. I have Xschem here, ls, and then Xschem. I'm not explaining much because in last 3 lecture we have mostly covered everything, right? So if you are feeling something missing, then please revise those. Yeah, so this was there. Okay, so before we do anything in Xschem, there is one theory, and which is very important, and that is the difference between propagation delay and the rise and fall time. Okay, so for that, let me bring up this page. I hope it is visible. Yeah, see, so the propagation delay, there is a simple definition we have, and that is you are giving some input. For example, here this is your input. This input could be your clock or could be a output of the previous block, right? This is our inverter block. So this inverter block could be fed by directly a clock, or could be fed by the output of another block, a previous block. So that is our input. So the simple definition is that any time you give a input, it will have a maximum value. For our case, it is 1.8. So from the 50% of that value to the output should reach the 50% of that. For example, if you are giving a high input value, which is 1.8, so what is the intended output? It should be 0, right? It should fall from 1.8 to 0, because it's the inverter. So that means from 0.9, 50% of 1.8 is 0.9. From 0.9 input to the 0.9 of output, what is the time we are taking? And that is your low side of propagation delay from high to low, because our output is going from high to low. And the same thing is true in the other side, and that is propagation delay from low to high. And the propagation delay, because we have two part here, right? High to low and low to high. Don't just ignore this those things for now, but for now just concentrate here only. So we have two part, probably both side will have the same delay, but most of the time they are not same, because the width of our PMOS and the width of our NMOS are not same, right? And charging time capacitor, like anytime you are getting from 0 to high output, we are charging our capacitance, load capacitance, and charging is mostly like we get the current through the PMOS. So that means going from low to high mostly depend on the size of PMOS, and reverse is true for the NMOS. So that's why these two sides won't be same. So that's why what we do, the propagation delay we take, and that is the average between the two, low side and high side. That is your propagation delay. Propagation delay actually have no physical consequence. Like propagation delay is not the delay time, actual delay time. For example, here let me mark something. Yeah, I have the, see, you have given your input in this time frame. So here if your input have no delay, that means at the exact moment we had 1.8 here. It is like that square wave, right? Which is not true here, but if it is, then so we are giving an input of 1.8 at 0, and if there is no delay, then at the same moment only we will have here the low output. So there means 0 delay. But what happening here, see, you are taking some time from here to here, right? And then you are again taking some time from going here to here, perfect, to delay component, and then your output again taking some time from going this 50% zone to the 0 zone. So that means we have 3 part, 1 part, here 2 part, and here the 3 part. So if you add these 3 part, that is your exact delay what we are facing here. But we take this propagation delay as a standard thing because, see, if we have 2 inverter back to back connected, right, back to back connect, so here for with respect to this inverter, the clock or the input would be the output of this inverter, right? So anytime the output of our first inverter, this is our first inverter, start rising to some value, we don't need to wait up to the full value, because if you remember the structure of your inverter, we are giving input here, right? So that means we don't need to wait up to 1.28. In some midway, actually this output, I have drawn this here, schematic here. So in some midway, the threshold voltage of this will be reached and this inverter will be active in our circuits. So that means we don't require the full delay from here to here, and that is little complicated to explain in the isolated scenario. So that's why we have a term, and that is your propagation delay. So that is the first term. It is 50% input, 50% output, the rough scenario we have said. If you want to go more deep into the theory, you can refer 1.3 of this book, 1.3 section of this book. They have explained it in more nice way, but we are not going deep into the theory because we want to do practical work here, right? So if propagation delay are all okay, great, then what is the rise time and fall time, and what is the importance of rise time and fall time? We will come to this thing little later. First, let's calculate our propagation delay of our design, what we have done. So from the last few videos, we have already done the DC analysis, right? So now give me the answer for today's scenario. Do we need to do DC analysis, or do we need to introduce the transient analysis here? And the answer is yeah, we need to have the transient analysis. Why? Because we are doing delay analysis, the dependency of time, and DC don't have any dependency on time, right? So that's why you need to introduce the transient analysis here. So for that, first we will edit this one, and we will edit another line here, and we will introduce a next type of simulation, and that is transient. And in transient, what we have, and that is, first we define the steps here, and then we define up to how much our time simulation will go. So let me define a smallest step, for example 0.02 nanosecond, and do it for 10 nanoseconds. Okay, so that is done. Okay, and now our V in was, because we were doing DC analysis, so we are changing V in here, but for now when we are doing transient, there is no control of V in, so let us fix this V in, and our V in will be a pulse, because we need to see the transient. So we will give a pulse to our inverter, and we will see it when it is going up, what is the delay analysis, like delay response. So for pulse, what I need to do, I just need to write here PULSE, and then what's the syntax of pulse. So I know it, but to let you know what you need to do, you need to go to your Ngspice manual, right? And after going there, Control F and write dot pulse. It's not searching. Yeah, it is now searching. Pulse, go more, somewhere it is full description is given, so you search it like this. Yeah, so see here pulse is there, so this is your start. From here you will start your pulse, and what's the top value of your pulse, we will get that. And then this is your delay, like after you start, like what's the delay, so mostly delay will give 0. Then the rise time and fall time of your pulse, I'll explain what is rise time and fall time, like after we do one of the simulation. And then the pulse width of your signal, and then the period of your signal, that pulse, and how many pulse you need. Okay, so that is the syntax. So I'll follow the syntax and I'll write it here. So first we'll start from 0, we'll go up to 1.8 volt. Delay time will give it 0. The rise time, let's give it very less, for example 0.3 nanosecond, and rise time and fall time same, 0.3 nanosecond. And the period, like the period, so for example 3 nanosecond. So if it is 3 nanosecond, then this is actually pulse width. So if pulse width is 3 nanosecond, then if you make a symmetrical pulse, then it will be, the period will be twice of your pulse, so most probably 6 nano, but it won't be twice. Here we won't get a but here we won't get a symmetric pulse because we have delay also, 0.3. So let me edit here 0.3, 0.6. So mostly we'll have a symmetric pulse, but these are okay, you can give anything. And after that, and then for how many pulse, so roughly 5 pulse, but actually this mostly controlled by this, for how much time we are running our transient analysis. So if you gave 100 and your transient analysis for 1 pulse, then it will show only 1 pulse. Okay, I hope I have done everything correctly. So okay, and then let's netlist it. But before netlisting it, let me go to view, as I told you earlier, option, and they are show netlist, so that we know netlist got created. Yeah, and everything got edited here. See, your VIN got edited and other things, so you can see it. Save and then simulate, and you're simulating. Okay, another interesting thing is you can see here we are doing 2 simulation, one is DC, another is transient, right? So VIN also 2, one is this VIN, another is this VIN. So to reduce the confusion, we have one command if we are doing more than one simulation, and that is your set plot. So if I just write set plot, it will show me how many plots we have. Like I have a transient, I have DC, and a constant. I don't know what is constant, but yeah. So here we'll write set plot, and as we need to see everything about trans, so we'll write trans 1. So now if something was, yeah, so now if I write plot VIN, then we will be sure that hey, VIN is coming from the pulse only, like what transient simulation defined. So let us see plot VIN, and see this is your input, and we can see some significance, rise time and fall time, right? And yeah, so it's good for our purpose actually. So this is VIN. So let us do one thing, VIN and V out, and see this is your VIN and V out. If I just get this portion, then this is looking very nice actually. From here we can easily find out our propagation delay, and propagation delay is reduce your VIN. So 50% of your VIN to the 50% of your V out. So 50% for only 0.9. So if I little zoom in more, then you can see, like from here we can directly identify actually from 0.9 to 0.9, it will be some significant amount of time. But as we are working on Ngspice, we have some powerful commands, so we will use those commands. So first we will measure something from trans analysis, and the variable would be in the input, like when my input is 50%, what's the time. So VIN 50%, what's the time. So I'll write when my VIN is equal to 0.9 volt, and see your V in, if I cross it, your V, let me cross it, these two, see your V in red one, only concentrate on red one, your V in becoming 90% many time. So which one, which time we need to define it, right? And for that we have a variable, and that is fall or rise, we can define. So I won't be considering the first one because first one mostly have junk value, so we will take the second one. But I want to calculate the lower side, when my input is going from high to low, our input is going down and then up, rise, and it is rising for the second time, first time here, second time. So here I'll rise equal to 2. I think everything's perfect. And see, so this is your V in. Now we will do the same thing for V out. When V out is your 50%, and when your V out is 0.9 and V out is falling for a second time, see red one, it's falling here, then rising, and then again falling. So perfect, and enter. So this is your V in. So now it's simple, just take the difference between these two and you got your lower side of propagation delay. So I'll do let. With let we define any variable, TP high to low equal to V out 50 minus V in 50, and to show the value we will write print TP high to low, and this is your value. And see, it is in pico, it's not in pico, but if we want to go in pico, then it is 24 picoseconds. So we have a significant propagation delay. So this is the lower part of the propagation delay. You can calculate for the higher side of the propagation delay and then take the average, we get our propagation delay, the perfect propagation delay. Like if anybody say find out propagation delay, or you can write this every explanation in your GitHub repository. You write in such a way so that if any other student is reading it, they can get everything what you are doing, and also it will help you in later part, right? Because you are doing a project now, and probably after 5 months, 6 months you have your interview. That time you can't do this project again. That time you can refer your Git repository, you can read your own explanation, and you can just give those explanation to your interviewer the next day. So that's why I write everything clearly. From now only keep on writing. After this project is done, we will see, like if you need help, I'll try to help you with GitHub, but you need to comment it down if you need the help. So now what's the issue with propagation delay? Because we have propagation delay, then and also we have the rise time and fall time. So what's the need of rise time and fall time? See, propagation delay is not independent. If I go to again to my this one, see here, this is your output, but the delay is depend on your input, right? And this input could be a clock, or this input could be an output of the previous block. To see the independent delay of your output, like we don't want to see what the input was there, is there any delay or not, then we need to take the help of the rise time and fall time, because rise time and fall time are independent of what input is coming, when the input is coming. So that's why rise time and fall time are used. And rise time and fall time again have many different definitions, but the most used definition, and that is from the 10% of your value. For example, in the falling side, so falling side would be the 90% of your value to the 10% of your value. Okay, so if it is 1.8, 90% would be 1.6. So when your output is at 1.6, to the time, what the time it is taking to go down to 10% of the maximum value, which is 0.18, and that is your falling time. True is same for a rising time. You may say, hey, why it is 10 to 90, why is not 30 to 100 or something? There are many explanations, but these things mostly depend on the threshold value of your MOSFET, because we need to see when our next MOSFET will get one. So if you want to deep dive into theory, you can, but today we won't. We will take this definition as it is. So now if fall time and rise time are clear for you, we will find those things also. But before that, let me show you how the dependency of propagation delay are in the clock. clock or the input side. For example, let me copy this thing to remember, and for that I'll get a sticky node here. Make our input faster. Here our input have a rise time and fall time of 0.3, but we'll make it little stiffer this time, 0.1 nanosecond. And we will see, like, we are expecting that there would be a change of propagation delay, and this will prove that hey, propagation delay has a dependency on the input side, right? So okay, and then netlist, save, close the simulation window, simulate it here. Oh, sticky node we lost. Why is the sticky node? Oh no, we haven't lost, thanks. Okay, so propagation is simulation is going on. So I have found these two things, and then let me do the let TP high to low equal to V out 50 minus V in 50, print TP high to low, and see, previously it was 2.4. if I bring it here, previously it was 2.4 because our input was slower, slope was more, but now we reduce the slope and then our propagation delay is also reduced. But this propagation delay is a great tool when we are dealing with a series of inverter or series of blocks, right? That time propagation delay really help us to know the delay of our circuits. But when we are doing anything individual, like here inverter analysis, then the rise time and fall time make more sense. So let me do that here. So for rise time and fall time, what we need, let me print V out for you so it will be clear. What I printed, not print, plot. Yeah, so if I just zoom in this section, so rise time and delay time is that from 90% to the 10% to the 90%. So let me define the 10% first. So V out 10% equal to, and it is, we know is if 1.8 is our highest, then it would be 0.18. Oh, we need to use let for defining a variable, and then let V out 90% as 1.6, right? 1.6. So that is done. Now we need to tell our SPICE simulator that hey, calculate the time. So for that we will again measure a value from transient analysis, and we will give it as time when our output is at 90, when V out is equal to V out, actually directly here only we can write 10% na 1.8. These two variables are not needed, directly I can define it here. And again we have many rise time and fall time, we need to define which one. So first one mostly we'll ignore, take from the second one, but this is the first time it is rising, right? So yeah, so when is first time rising, tran T10, when V out is this, first time it is rising. I think I am not missing anything. Yeah, so this is your T10, and let us define T90 also. And when your V out is 1.6 and the rise time is same thing, so this is, and to find out the rise time, TR equal to, it would be T90 minus T10, and don't forget to add a let before to define that particular variable, and then pre-TR, and this is your TR. So let me copy it here. So this is your rise time. Fall time also we can calculate, but it's your task to calculate the fall time.